So, hey guys, my name's Brandon Adler. I'm doing a presentation on Yuffie Secure Boot. Who am I? I'm an old man now, new alum, just graduated in May, old ops lead. I love to red team still, and I'm scuzzy on Workplace and Discord. So, just a quick intro to Yuffie for those who aren't quite familiar or have heard of it but don't know what the difference is between it and BIOS, because it was kind of the replacement for BIOS. And it's actually much more complicated. So it does all the hardware initialization and booting the OS or first stage bootloader on top of going through a whole security phase. There's actually a modular driver system built into Yuffie that didn't exist in BIOS. And that kind of adds to the extendability of it, which is kind of interesting. So for this flow chart down at the bottom here, so the security phase just does initial firmware integrity checks, nothing too crazy. The second stage initializes the CPU and begins the process of secure boot. The DXE phase, or the driver execution environment phase, just starts hardware initialization and all those modules that actually communicate with hardware potentially. The boot device select phase is exactly what you think. It initializes the boot manager for selecting, do I want to boot off a thumb drive, hard drive, or the network? And then it could potentially start the bootloader, and then the bootloader then starts the actual kernel for your OS. So an overview of secure boot before we get into more of a dive here. It's actually a system that adds a lot of verification to the boot chain of your computer. So it actually verifies your bootloader, your kernel, and anything in between, any drivers actually that exist in Yuffie to prevent them from starting if they're not signed or if they're malicious. It's fully supported on Windows. You can basically, anybody running Windows, you can literally just go into Windows 10, I should say. You can just go into your BIOS and enable it if it's not enabled by default, and it should just work out the box. It works on Linux, but it's definitely more of a pain to get set up and to get working functionally. And I'll get into more of that later. But it's honestly, it's a pretty low bar of entry to preventing low-level attacks. And throughout the presentation, you can kind of gauge if it'll be of benefit to you or not. So what does secure boot really prevent? So bootkits. So we don't usually like people replacing Grub or our bootloader with another one that's malicious, right? Because if the bootloader is compromised, then basically anything that starts that runs after the bootloader, like your kernel applications, even running in your kernel or user space, those are basically compromised or could be theoretically. Kernel level tampering. So if you modify the kernel and a malicious one is placed on your machine, then they have full OS access, full root, full system to your machine automatically. Modifications with physical access, like booting off a USB. So if, let's say, your hard drive's not encrypted, right, somebody could literally just boot off a USB, replace the kernel, or really any application in your system, and you're basically compromised. And if anybody of you have, definitely ThinkPads have this for sure, LoJax or CompuTrace, if you ever look at your BIOS settings. So that actually gets disabled when you enable secure boot. And I'm going to go to a nice diagram here. And that's because it's not actually signed. So this is kind of like a short excerpt of the DXE phase that your BIOS or Yuffie would go through when executing. And the LoJack right here, the LoJax module, and there's a Yuffie shell too that you can use to do some low-level interaction with actually Yuffie from like a command prompt like shell. Neither of those would function off the bat when enabling secure boot because they're just not signed by basically Microsoft. We'll get into that a little later, but as an example, like these are other modules that exist in the DXE phase that Yuffie has to initialize before you're able to use them, like audio, USB, GPU, any PCI cards you have that need to be running. So really the bread and butter of secure boot is this public key cryptography. So there's four main things and some additionals for Linux that we'll get into in a sec. But so the platform key is basically the master key of secure boot. It should be unique per device, and it signs the changes made to the key exchange keys, or it can directly sign this allow list database or deny list database itself. But usually that's not best practice, and it absolutely cannot be used to sign binaries like grub or the kernel or anything like that. It's only meant for these lower level uh, files, I'm going to call them, but they're really like variables in UEFI. So the key exchange keys are a list of keys that people like your vendor, Microsoft, and manufacturers will put in that allow them to make changes to the database. So let's say if your, you know, hard drive changes, they can potentially have that be validated in secure boot, in the sequence of secure boot. So so that's basically all like as soon as your laptop ships out, they already know their hardware, so they put it in this database. So the database also contains a list of public key certificates, as well as potential SHA-256 hashes of binaries. That makes it a little easier instead of using full certificates, but mostly certificates are used for this part. And this is basically just these certificates are allowed or actually checked if against like grub or whatever is being verified next. And this denied list database is the ultimate veto power. So it basically just means it's the first thing that's checked, and if the hash or certificate that like your kernel is signed with exists in this database, then it's automatically denied the ability to boot, which is kind of interesting and pretty much how it should be. Since if it gets compromised and it gets revoked, the vendor or Microsoft, your OS will actually put an entry for that modified or malicious or vulnerable kernel in this database, so it can't be used ever again. So this is just a little flow chart to just visualize how the signing process works with Secure Boot. So the PK is the platform key, and that'll sign the key exchange keys, the list of key exchange keys. And then from that, the key exchange keys are used to sign both of the databases. And it just makes it easy for vendors or anything like that. If you have multiple keys that need to sign the database or DBX, like your manufacturer is usually the one to insert or generate the platform key, which could be Dell, right? And the key exchange key, they could also have a cert for Dell or Microsoft, both of them actually in there. So then they can use those keys to sign anything to validate against changes that they have to make in the DB. Like if your bootloader changes because Microsoft got an update, that needs to be in the DB. So for Linux, it gets a little more interesting. So Linux has the machine owner key, that's what MOC stands for. And that's only used on the Linux implementation. And why is that? There's a shim that Microsoft actually signs that allows Linux, I should say grub, to actually be used. So the shim is signed by Microsoft, and Canonical actually made the shim so that they'd be the main ones to maintain that, because they wanted it for Ubuntu. They wanted Ubuntu to be able to secure boot relatively easily. So Microsoft doesn't want to sign grub or other bootloaders, because there's quite a few other bootloaders that anybody on running Linux can use every release of those bootloaders. So they were kind of like, they made a stopgap, and they're like, okay, so we'll let them make like a little in between, a shim that then starts grub. And the mock X down here in the flowchart, that's a deny database similar to the DBX. And the mock is similar to the regular DB, but they're additions made because of the shim that I actually think I talk about this in the next one. So cool thing about the mock is it allows users to add their signing key to the mock. So if you're running Linux, it's basically required. But if you're running anything besides Ubuntu, it's absolutely required because let's say Fedora, right? They don't actually have a grub, a bootloader that's signed by Canonical, and the shim checks if the bootloader is signed by Canonical or Ubuntu. So that's why you have to if you're running Fedora, you're going to have to sign both the bootloader, the kernel, and any kernel modules that you want to load. And you'll have to sign kernel modules for Ubuntu, but if you don't use any that aren't already signed or have valid signatures, then you're probably okay. You don't really need to make one. But since the shim checks against these signatures in the mock DB, if you want to run a kernel module like NVIDIA, I think I talk about this later too, but then you literally need to put a key in there for the shim and the kernel to validate against, because the kernel also looks at this mock DB and determines if a kernel module should be loaded or denied. And a good thing to note about this mock, the machine owner key portion, is it's not part of the secure boot standard. So this was kind of up to Microsoft, Ubuntu, and Intel to decide amongst themselves about what the best way to go about was for Linux. And this is what they came up with, but they still didn't put it in the standard. And just a quick mention too. So I mentioned Intel, right? That's I don't even have Intel in this presentation, but they actually are full maintainers of the UEFI standard. So since Secure Boot is under that, they actually maintain the Secure Boot standard as well, along with any code that goes along with that. And they do have an open source UEFI implementation, which is kind of neat. So Linux. Thankfully, the shim itself is pretty easy to install. It's literally as easy as an apt-get install on Ubuntu. But if you're not running Ubuntu, you do have to sign your kernel and kernel modules every time they get updated. So this is a real pain because things like VMware, Oracle, VirtualBox, and NVIDIA drivers, kernel modules, are not signed by those developers. So it's a really big pain when you try to install some new software that you need for work or school, and then those kernels actually get denied by the kernel to load since they're not signed. So that's kind of one of the cool things about the mock, like I was mentioning earlier. So all that sounds great, right? We're going to prevent people from, modifying our bootloader, modifying our kernel, and getting in the middle of our boot sequence. But who can we trust to actually prevent that, right? Who can we trust to keep us secure? And right now, it's in this ecosystem, it's mostly Microsoft. They actually sign all the low-level components for most of the software components and even some of the hardware components that are running in UEFI and post UEFI. And some vendors and manufacturers, as we can see in the diagram below, they are usually the ones to generate the platform key, which that's kind of like the necessary thing for this whole system to work. So if the platform key gets compromised, they can a malicious actor can basically add their own key to the KEK, the kernel exchange key, or the key exchange keys, and then add their own entries to the database to allow their software to run. And that's why multiple computers should not have the same platform key. Because again, if there's multiple of these keys out there, right, or I should say the same key that's used on, let's say, 100 machines, that just helps somebody compromise it that much quicker if they actually do compromise it. So it's funny because on Linux, it's still Microsoft's job. You still have to trust Microsoft for secure boot to actually be secure. But then, in addition to even Microsoft and your manufacturers of your laptop or computer, you also have to trust Canonical, since they sign their grub and their kernel releases. So that's just like another certificate that has to be kept secure in order for this whole process to work. So the big fix for that actually a lot of companies that deal with, nation state actors and people who will spend a lot of money to compromise this company, they actually use custom signing keys, custom keys for secure boot. And the interesting part about this is that it is slightly more secure if these keys are if these keys are generated properly and then kept in a secure environment, the private keys, since it just reduces the overall keys in this chain. And since they are the ones that actually maintain that, let's say they just throw literally hard copies potentially in like a safe, right, or an encrypted hard drive somewhere, then that's basically the only way, one of the only ways you could copy that, you could compromise secure boot in this instance. So that's kind of interesting, and that's actually one of my goals to do in like the next couple of months, is to generate my own keys for secure boot. So since we're talking about all the security, it's all great and everything, so there's always small little pitfalls that come around with this, right? So probably the biggest one, in my opinion, is vendor specific implementations. So as soon as you have a standard, there's things that potentially aren't covered in the standard, right? So one of these is when does UEFI actually have to verify specific components? So if you have secure boot enabled, but then you have fast boot also enabled, it is up to the vendor or motherboard manufacturer to actually check all of those individual components during the secure boot phase. So there was a problem in some manufacturers where if you have fast boot enabled, that barely even does verification on the boot chain. So at that point, you basically don't even have secure boot enabled. So it's kind of like it's pretty bad, because then you think you're secure, but you're really not, and that's just because of their implementation, and that's kind of tough to figure out as well. Another huge one is actually a lot of motherboard manufacturers are starting to force this, which is good. So if you enable secure boot now, you almost certainly have to set a supervisor password for UEFI, which prevents people from just pressing F2 when your computer starts up and disabling secure boot. You have to enter a password that then lets you into your BIOS or UEFI to then change settings, which is super nice. Some software actually does catch this, like BitLocker and Lux, and that's because they use a specific function of the trusted platform module that exists or hopefully exists in that laptop or computer. And that's even that interaction is probably a whole nother presentation, but I just thought it was important to mention that as well. It's still important to encrypt your hard drive, because since this only verifies the boot chain, if you're running Windows or Linux, your normal partition where all your data stored can still be modified, and Linux or Windows will just execute, whatever script that somebody will put there, depending on the directory you put it in, which is, it's still a problem. So I would say everybody still should be encrypting their hard drives, even if you enable this. And there have been vulns in this. There haven't been too many, but unfortunately, many of the vulns have been because of, there's so many different manufacturers in the supply chain, really, for secure boot that you have to depend on to do it right, that inevitably somebody's going to mess it up, and then the whole system is compromised. So that's really one of the downfalls of secure boot. And that's really all I got for Secure Boot. Does anybody have any questions? And John, I don't really know how to take questions, so if anybody does, let me know.